For years, scientists assumed the sun was a good model for understanding how other stars behave. Solar flares and sunspots rise and fall together on our sun, and that pattern was expected to apply across the galaxy. But new observations tell a different story. A large study using space-based data shows that, for most stars, flares occur without any clear link to star spots. This suggests the sun may be an exception rather than the rule. In this video, we will examine what was discovered, how it was measured, and why it matters. Let's get started. The results come from a large statistical study of stellar brightness variations observed by the Transiting Exoplanet Survey satellite, commonly known as TESS. Although the mission's primary goal is to detect exoplanets, its ability to monitor thousands of stars continuously makes it well-suited for studying stellar activity. Because astronomers cannot directly image the surfaces of most stars, star spots must be inferred indirectly. As a star rotates, darker magnetic regions on its surface cause small but regular dips in brightness. These periodic changes reveal when star spots are facing toward or away from Earth. Stellar flares appear very differently. They show up as brief, sharp increases in brightness caused by sudden releases of magnetic energy. Since flares can only be seen on the side of the star facing us, their timing can be compared with the rotational phase inferred from brightness modulation. Using this method, researchers analyzed more than 14,000 stars and identified over 200,000 individual flares. With such a large and uniform dataset, even weak relationships between star spots and flares should be detectable. For the sun, the expected pattern is clear. Solar flares almost always occur near active sunspot regions. If other stars behaved similarly, flares would tend to cluster at the same rotational phases where star spots are visible. Instead, the data showed no such pattern. Across the stellar sample, flares were just as likely to occur when star spots were hidden as when they were facing Earth. Roughly half of all detected flares showed no association with star spot facing phases at all. From a statistical perspective, the correlation was indistinguishable from random chance. This result was not confined to a small subset of stars. It appeared consistently across a wide range of stellar rotation periods and activity levels. Given the size of the dataset, the finding is unlikely to be explained by observational noise or selection effects. The central observational conclusion is simple but significant. The tight relationship between spots and flares seen on the sun does not appear to be common among other stars. Star spots and flares are both expressions of magnetic activity generated inside a star by its dynamo. On the sun, this dynamo produces relatively organized magnetic structures that rise to the surface as sunspots. When magnetic field lines in these regions become stressed and unstable, they reconnect and release energy in the form of flares. Because this connection is so clear on the sun, it has strongly influenced how stellar magnetic activity is modeled. Many theories implicitly assume that visible surface features and energetic outbursts are closely linked. The new results challenge that assumption. One possible explanation is that many stars generate magnetic fields with surface geometries different from the sun's. Instead of producing large, long-lived spots, their magnetic fields may emerge in smaller or more distributed structures. These could store and release energy without causing strong, periodic brightness variations. Another possibility is that flare-producing magnetic regions are not always anchored near the stellar surface. In some stars, magnetic energy may be stored deeper within the convection zone, allowing flares to occur without a clear surface signature. Rotation likely plays an important role as well. Many stars rotate more rapidly than the sun, and faster rotation can lead to more complex and less ordered magnetic fields. In such environments, the spatial relationship between spots and flares may break down. What makes the sun stand out is not simply that it produces flares, but that it does so in a highly organized way. Its spots are long-lived, its magnetic cycle is relatively stable, and its flares are closely tied to visible surface activity. Rather than being typical, The Sun may occupy a narrow region of parameter space where magnetic structures are both stable enough to form spots and dynamic enough to produce frequent flares in the same locations. At present, no single theory fully explains why this configuration appears to be uncommon. What the study demonstrates is that stellar magnetism is more varied than previously assumed, and that solar behavior should not be treated as a universal template. One immediate implication is that astronomers must be cautious when generalizing from the Sun to other stars. Solar-based assumptions are often used when direct magnetic measurements are unavailable, but this study shows that those assumptions can fail. The findings also affect how scientists think about stellar space weather. Flares can influence planetary atmospheres through radiation and energetic particles. If flare activity is not linked to starspot cycles, then predicting flare behavior becomes more difficult. This has important consequences for exoplanet studies. A star that appears magnetically quiet based on spot-related brightness variations could still produce frequent flares. Conversely, strong brightness modulation does not necessarily indicate high flare activity. From a theoretical perspective, stellar dynamo models will need to account for multiple magnetic regimes. Some stars clearly produce flares without prominent surface spots, while others, like the Sun, show a strong connection between the two. Future progress will likely come from combining different types of observations. Photometric data can be paired with spectroscopic and polarimetric measurements to probe magnetic field strength and geometry more directly. Longer monitoring periods may also reveal whether correlations change over different activity cycles. Rather than focusing on how closely other stars resemble the Sun, researchers are increasingly interested in mapping the full range of magnetic behaviors stars can exhibit. In that broader context, the Sun becomes one example among many, rather than the standard against which all others are measured. The study shows that the Sun's tight link between spots and flares is not typical among stars. For most stars, flares occur independently of visible surface activity. This challenges long-held assumptions and reshapes how we understand stellar magnetism.